start? Okay, hi everyone. Thanks Ron for the great talk. I'm gonna repeat some of the stuff for the people back home joining just for this video. My name is Eylon Yogev, and as opposed to the bad news that Ron gave us today, I'm gonna try to give us some optimistic good news, and also we will talk about this. Okay, so let me kind of recap the stage that we're at, okay, in maybe simpler terms, okay, without going into particulars of the GKR protocol and stuff like that. So I'm going to be focused on very simple protocols. I call them Sigma protocols, okay? What I mean is just 3 message protocols, and I want them to be public coin. And we're also going to consider this pre-processing setting, exactly like Ron described. So I have a prover, and the prover says, oh, I know a witness, a W, such as this circuit, C of W equals Y. And the verifier is going to get this psi, okay, psi, this digest of the circuit, and we're going to have a 3-message protocol. So the prover is going to send some message M1, this is the first message of the protocol. The verifier is going to respond with some public randomness. Here I'm going to call it just rho. And then once the prover has rho, okay, she can send the second message, okay, which is some function of rho, M2. And after the verifier has all this information, the verifier wants some decision algorithm, okay, so this is V, the verifier Sigma protocol, VSP. So what is the information that the verifier has? The psi, the Y, the M1, rho, and M2, okay, run some decision algorithm and it either accepts or rejects. Okay, so these are Sigma protocols. I'm going to distinguish between 2 things. We have statistical soundness, which means that these protocols are sound against unbounded provers. Okay, we call this a proof system. And we have computationally soundness, where the security holds against computationally bounded provers. Okay, this is an argument scheme. Okay, so what is the Fiat-Shamir transformation? Like Ron described, it's a way to compile interactive protocols into non-interactive protocols. So we're gonna compile this small 3-message protocol to be non-interactive. We have some Fiat-Shamir hash, some hash function H, and the prover is gonna compute the same M1 as before. It's gonna derive the randomness using the Fiat-Shamir hash. So it's gonna hash psi, Y, and M1. This is all the information that the verifier has. And then it gets the randomness rho. Now that it has rho, it can derive the second message M2 and just send all of this in one shot to the verifier. What does the verifier do? Well, it derives the same randomness rho and then runs the exact same decision algorithm that it had before. Okay, so this is how I compile the Fiat-Shamir transformation on Sigma protocols. As you all know, this is a transformation that is well deployed in practice and is currently protecting billions of dollars in signature schemes, snarks, blockchains, and more. And we really need to study the security of this transformation. Okay. So, as also Ron mentioned, Poncheval and Stern proved that this transformation is secure in the random oracle model. Okay. And it's proven both for proofs and argument, okay? For proof systems, actually we have a long line of work showing that there exist hash functions that make this transformation secure. So at least we have some nice evidence of this transformation, okay? For argument system, the situation is not so simple, okay? And what happens, as Ron described, we have all of these attacks that work against these argument schemes. So what are these attacks? These are really strong attacks. They're showing that you have a Sigma protocol, you have an interactive protocol. This protocol becomes insecure regardless of the implementation of the function H. Okay, so for any white box implementation, okay, for any circuit that implements this function H, the protocol becomes insecure after you apply the Fiat-Shamir transformation. Okay. examples of attacks. This is the Barak and God versus Kalai, okay? Other examples as on described, this is on the Eylon protocol of PCPs or IOPs when you compile them. And obviously, the recent attack on GKR, which is really a natural attack. And I would like to say, we didn't coordinate the slides, but I have the same scratch on here. Maybe great mind things alike, but okay. So you can see that this really had some effect on practice. And the worry is actually that, this attack could be further developed and have more and more effect on practical systems. I would like to give some positive news, okay? We have no attack unlike the Schnorr protocol. So the Schnorr protocol is kind of very specific and doesn't have a lot of room to play with. So currently these attacks do not affect things like the Schnorr protocol. Okay. So let me start by describing our result. So we provide a new transformation, okay? We call it XFS, this is extended Fiat-Shamir. And it's aimed, and I want to emphasize the word aimed, okay, to mitigate white box attacks, okay? When I say white box attacks, these are the deorganization attacks, attacks such as the one Ron talked about, okay? Our solution focuses on practicality, okay? It has a negligible overhead on the running time of the prover and the size of and the communication size. It managed to circumvent the GKR attack, okay? So at least I don't know how to take the GKR attack and make it work on XFS, okay? We also provide some more reliable security. So we give some evidence. So we define a relativized model. And if I have time, I'll talk about it in the end. But this is a model where it's actually an ideal model, like the random oracle model, and we're going to have a random oracle. However, in this model, the Fiat-Shamir transformation is actually not secure, okay? As opposed to the random oracle, where we can prove that the Fiat-Shamir transformation is secure. So you have a model where the Fiat-Shamir transformation is not secure. However, our XFS transformation is provably secure in this idealized model, okay? So this gives us some assurance of security, at least in the sense that if you want to develop a new attack on XFS, you should look at this model and say, oh, this attack, is it captured by this model or not? If the attack can be mounted inside the model, then it won't work, okay? So any attack kind of has to reinvent itself and be somewhat outside of this model, okay? I'll also say that our XFS doesn't protect against all the attacks we know, okay? In particular, it doesn't protect against these attacks that we talked about, the Barak and Eylon and the God versus Kalai. So these attacks still work for Fiat-Shamir and for our transformation. However, these attacks are much more contrived, and the GKR one, which is natural, is kind of defended against. Okay. At this point, before I continue, I just want to say that my main point here is that we have this cat and mouse now attack and defense, and I just think this sheds a lot of light that this is kind of becoming a new area of research. I need much more eyeballs and new techniques, okay, to fully understand Fiat-Shamir and its security. Okay. So what I'm going to do, I'm going to kind of recap and show you a toy protocol where we can attack, and then I want to show you how the XFS transformation mitigates this attack. Okay. The good news is it's going to be a much simpler attack, so I'm abstracting many things away. Okay, so it's not going to be the full GKR attack, something much simpler. Okay, but it's just a toy protocol. Obviously, this is kind of a contrived example. Okay, so here's our prover and here's our verifier. And we're going to have some CORM, some commitment scheme, okay? And the digest of the circuit is just going to be a commitment to the circuit, okay? So this is what the verifier gets, just a commitment to the circuit. The prover is going to send M1, which is just a commitment to the witness, okay? The verifier is going to send some randomness row. Now what is the prover going to do? It's going to decommit to C and W, okay? So decommit to the circuit and decommit to the witness, okay? Okay, this is a bit silly. The prover is just sending the entire circuit and witness, okay? And the verifier is just going to check that C on W equals Y, okay? So this is a completely trivial protocol where the verifier just does all the work by himself, except we're going to add this trapdoor. We're going to say either C of W equals Y or the circuit that you already committed to in the pre-processing on the witness that you already committed to in the first message equals 1 concatenated with row, and we'll explain why we need this one, but just think of the row, okay? So somehow the prover managed to predict row in advance. Okay? So this is the type protocol. What does this protocol satisfy? Well, completeness. Obviously, the honest prover is just gonna commit to valid circuits and witnesses, and the verifier is gonna accept because of the first condition. Okay? And also, this protocol is sound. Okay? So if the statement is false, then you cannot convince the verifier by the first condition. You can also not convince the verifier by the trapdoor that we added, because there's no way that if you're computationally bounded, so you're committed, you have computationally binding to the commitment scheme. You're committed to the circuit C, you're committed to W already at this point. Now the verifier is going to choose a random row. Okay, there's just a negligible chance that the C and W is going to predict row. Okay, so this protocol is an argument scheme, has computational soundness. Okay. What happens to this protocol after we apply Fiat-Shamir? Okay. So we're going to send M1, and we're going to send the decommitment C and W all in one shot. Okay. And what is the verifier going to do? He's going to do the exact same thing, only he's going to derive the randomness row using the Fiat-Shamir hash on the digest, okay, and Y and M1. Okay, so this is the compiled protocol. Good. This protocol, after we compiled, is actually insecure. So what I'm going to show in a second is that for any function h, regardless of what this function h is, okay, SHA-256, SHA-3500, doesn't matter, okay, SHA in 1,000 years from now, okay, there is a prover strategy such that for any W, this circuit on W is not going to be equal to Y. However, the verifier is going to accept actually with probability 1. Okay, good. What is this circuit? Well, I just thank Ron for like presenting all the difficult stuff already. So this is kind of a rehash of this. Okay, so we're gonna, and these ideas, of course, stem already from Barak, but kind of everything is taken from Ron's paper. We have the circuit that gets a witness W, okay? So I need to present a prover strategy. So I'm gonna present a circuit and then a witness and Y such that the verifier is gonna accept, okay? So the circuit is gonna parse the witness as this digest, okay? Digest of what? Oh, it's the digest of the circuit itself, exactly this circularity thing that Ron talked about, okay? And Y. We're gonna compute the commitment to W, okay, which we'll call M1. And then we're going to output 1 concatenated with the hash of the digest that we have here, Y that we have here, and M1 that we computed here. Okay, so this is the circuit. Good. Let's see that we satisfy the conditions that we wanted. Okay, and Y is going to be the all 0 string. Okay, so just a long 0 string. The digest is going to be just the commitment to this circuit C. Okay, and then the witness is just going to be the concatenation of this digest, okay, and Y, which is just a bunch of zeros. Okay, so notice that Y is the all 0 string, and the circuit always outputs something that starts with 1, right? So no matter what witness we give it, okay, C of W is going to be different than Y. Okay, so this is a truly false statement. Okay. I remind you the focus today is going to be on proving true things, okay, not false things. We're going to start with a false example. Good. Why does the verifier accept? So let's look now at the trapdoor, right? Okay, so obviously the verifier is going to accept because of the trapdoor. So the verifier is going to compute C of W and is going to compare it to 1 concatenated with rho. C on W, okay, is exactly, okay, the output of the circuit, which is exactly this thing, okay? And this purple hash that we computed here is exactly the same hash that we have here, okay? So it's exactly 1 concatenated with rho. Okay, so the verifier is gonna accept probability 1, okay? And this protocol is insecure, okay? In a nutshell, when we had rounds, kind of, there was no way for the prover to predict the verifier rho of the randomness. But when you give me a Fiat-Shamir hash function, obviously I can predict. I have the code, okay? I'm going to commit to this code, and this is kind of the way that we predict this function. There's some circularity issues here, and exactly we solve them using this commitment to the witness. Okay. So the main problem was that the circuit C had to compute the randomness rho, the Fiat-Shamir randomness, okay, by itself, okay? So it had to compute the verifier next message rho, okay? That was the problem. And one naive solution, obviously, is to make the function H more complicated, more complex than the circuit C, okay? Such as kind of, it cannot do it. What are the drawbacks of this solution? So first, well, you're making it slow, right? If I make the hash function more complex, the verifier needs to compute the hash function, okay? So you're making the protocol, the verifier, slower. If we're talking about recursive composition, then I made the verifier slower, and then in the next round of my recursion, the statement that I'm proving is actually the verifier. So now I need another Fiat-Shamir that is more complicated than that, and so on and so on. So it's not very recursive friendly. Okay. And the third point that I want to stress is kind of, fine, let's say I'm fine with a slow verifier. I'm not sure still about the security of this system. Okay, so the Fiat-Shamir hash is more complicated. Is this secure? Okay. And actually the point is that it's more delicate than that. And we're going to see this in a second. Okay, so what we do, we propose an alternative solution. We're going to use some strong variant of proof of work, which I'm going to define, okay? And the intuition is that we're going to make the Fiat-Shamir hash function H very, very hard to compute, so it's going to be very complex and complicated. However, it's going to be very easy to verify. So the verifier doesn't need to compute this hash function by itself, it only needs to be able to verify it, okay? So the deterministic complexity of H is going to be large, but the non-deterministic complexity of H is going to be small. Okay. So let's start by just seeing the XFS transformation. And to describe the transformation, I just need a proof of work. And so I'm just going to define the notion of proof of work that I need. So a proof of work is going to be parameterized by some hardness parameter L, okay? Think of L as being 2 to the 20, okay? Something mediumly hard. This is something that the prover should be able to compute. So it's not like 2 to the lambda, it's not 2 to the 100. We have two algorithms. Solve is something that gets a puzzle, Z. So Z is like our challenge, our puzzle, and then defines something we need to solve. And we have an algorithm that solves the puzzle in time L. And check that gets a puzzle and a solution and can very quickly verify that the solution is correct. Okay? These are the completeness properties of kind of any proof of work. The security that we want is that we have negligible in lambda, negligible probability, okay, of solving the puzzle if you run in time less than L. Okay? Even if you have preprocessing, let me define this more accurately. You have an algorithm, so this is kind of this big algorithm. It runs in time much, much bigger than L, but it's a pre-processing algorithm. It doesn't know the puzzle Z. So it runs in some large time and produces some state, okay? And yeah, maybe gets some public parameters if your proof of work has a setup, okay? If it doesn't, then it doesn't. Good, so it passes on some auxiliary state. Now you have a second algorithm. This is a small algorithm. This is an algorithm that runs in time less than L, okay? So this algorithm is not supposed to be able to solve the puzzle. even though it got the auxiliary state of somebody that ran in time more than L, but this guy ran before the puzzle was chosen. So a puzzle is freshly chosen, given to this small algorithm, okay? It has time t2 that is less than L, okay? And we want that this algorithm, the probability that it produces a solution that is valid is gonna be negligible in lambda, okay? So kind of very, very small probability. So this is the security that we want from the puzzle. And let me compare it to stuff that you might know of. So our strong notion of proof of work is actually stronger than kind of the common known, the Bitcoin proof of work, of just finding a salt that hashes to sufficiently many zeros, okay? And well, maybe I already say, so the main reason is that for kind of the Bitcoin proof of work, I can always solve a Bitcoin proof of work in O of 1 time just by guessing a solution, and I will be right with probability 1 over L, okay? And we want that if you run in time less than L, your probability is kind of negligible. I don't want you to succeed with probability 2 to the minus 20, okay? If you didn't run in enough time, your probability is 2 to the minus 100, okay? So it's a stronger notion than the Bitcoin proof of work, but actually it's a weaker notion than maybe something, the proof of sequential work, which is actually weaker than verifiable delay functions, VDFs, okay? So it's a weaker notion than sequential work. Sequential work would suffice, okay? And stronger than Bitcoin proof of work. And we actually give 2 different constructions of this proof of work with kind of 5 minutes, okay? With trade-offs between the size of the solution. Okay. So let's now see the transformation, okay? So the prover is gonna choose the first message M1, okay? Now, before the prover has the permission to derive the randomness rho for the verifier, he first needs to derive kind of in a Fiat-Shamir manner, derive the puzzle Z that we want to solve. After we have the puzzle Z, okay, we solve it and get the solution S, and only after we have the solution S, we're kind of allowed to do the Fiat-Shamir hash, okay? So we're gonna hash as before, only we concatenate now the solution S. And this allows us to get rho. Okay, and then we can compute M2. And now we're sending everything to the verifier, so M1, M2 as before, and the new solution S. What does the verifier do? Well, the verifier can derive the puzzle in the same way. That's easy. The verifier can now derive rho, right? Because he has the solution, so he can derive rho. He's going to do the same decision algorithm that he did before, and one extra step, he needs to check the solution to the proof of work. Okay, so he's going to check this. Okay, so this is the new transformation. Okay. Let's see what happens for this new transformation on the toy protocol that we saw before. Okay, so remember the toy protocol, we kind of just committed to everything and then decommitted to it. Okay, and we had the counter example. And we can ask, does this attack work on XFS? Okay, so we need to modify the circuit C now to compute rho, right? If we want the circuit to attack. Okay, so fix any Fiat-Shamir hash function. Okay, this is the compiled protocol with XFS. Okay, now added the puzzle and added the check to the solution. Let's modify the circuit to compute rho. So we're going to parse as before. We're going to compute M1. Now we're going to compute the puzzle Z. Okay, no problem. We can do it. We're going to solve Z and get S. And now we're going to output this. Okay. This circuit now, just as before, is going to compute rho and convince the verifier. So what do? The only thing, and the same setting as before. What we do, we put the hardness of the proof of work L to be larger than the size of the circuit. Okay. So the prover should first decide on some circuit, or circuit size at least, and after we have the size of the circuit, we can define L to be slightly larger than C. If L is larger than C, then there's no way that this circuit computes the puzzle, okay, solves the puzzle. Okay, so it cannot run this thing, okay, and be the same size. Okay, you could say, wait, but maybe the witness that the circuit gets can help it solve the puzzle, right? Like before, we encoded things inside the witness, okay? But just you have to observe that when the puzzle Z is computed, okay, it's computed as the hash of these things, and this is the hash of the circuit, okay? And M1 is the commitment of the witness, okay? So the prover first needs to commit to the circuit and the witness, and only then kind of we Fiat-Shamir and get the puzzle Z. Okay. I don't have much time, so I'm just gonna end with one slide about what provably security we have. So we define this idealized model, a relativized model, okay, where we have a random oracle H, okay, but opposed to how people have proved Fiat-Shamir, where they kind of assume that we have some sigma protocol and then we add a random oracle H. We're going to have this random oracle H, and we're going to have all parties have oracle access to H. So the prover has oracle access to H, the verifier has oracle access to H, and the circuit has oracle access to H. So the circuit has NOT gates, AND gates, OR gates, and H gates, okay? So the circuit can have a gate to compute the random oracle. And this is all before, in the sigma protocol, before we compiled. Now we're going to compile this using XFH, okay? We're going to compile this with the same hash function H. We're not introducing some new function, okay? Good. So first, let's just look at the circuit we had before, okay? The circuit we had before, it only needed oracle access to H, right? Okay. Also needed to compute a commitment. Maybe although this commitment had oracle access to H. So we can actually mount the same toy example we had before inside this model. We didn't actually need the code of H. We only needed that the circuit had oracle access to H. And in this model, we can actually have the same attack. So in this model, Fiat-Shamir is not secure. Okay. However, what we can prove is that in this model, we have the following theorem, okay? The XFS star, there's some modification that we need to do that I didn't talk about, okay? If you give it a sigma protocol, okay, just a 3-message protocol, a public coin 3-message protocol, with something called round-by-round knowledge soundness, okay? But just a knowledge sound secure, let's forget about the round-by-round, okay? Kappa, and you give it a strong proof of work with some error epsilon, okay? This is kind of the probability that someone will solve the proof of work with small time. Then the XFS transformation outputs a non-interactive protocol with error O of T times kappa plus T times epsilon, where T is the number of queries or the running time of the malicious prover, okay? So kind of this is what you would expect from a standard Fiat-Shamir transformation, and we have this added error here, okay? And yeah, the XFS star is a slight modification of what we saw, and I won't have time to talk about this, so I'll just move forward.
Where can we read about it?
Yeah, it's online. You can.
Online?
Yeah.
And you published it in, or you got accepted in?
It's submitted, yeah.
Submitted.
Yeah.
Awesome.
Okay, so just a short summary. We saw that the Fiat-Shamir is actually insecure, and Ron talked about this in more depth. We proposed XFS as a way to mitigate these solutions, at least mitigate this GKR attack, at least for now until kind of the next version. We used a strong proof of work, and I didn't have time to show you how we construct these strong proof of works. And we have some, heuristic, at least, proof of security in a relativized model. Well, it's a proof in the relativized model, but it's a heuristic sense of security. Some future work. So I only talked about 3-message protocol and kind of not extremely trivial how to extend this to multi-round. It's kind of ongoing work. You can maybe, instead of the relative models, talk about stronger models, kind of algebraic models, and prove security of the XFS transformation in those models. Okay, that would actually be able to completely mount the GKR attack. Okay, you can do an analyze of this Fiat-Shamir with sponges. Kind of we assume a completely random function. In reality, we kind of don't have completely random functions. We do this response construction, and it changes the way you need to prove security. Okay, that's it. Thank you.